Greetings everybody, and today we're going to be taking a look at bases for topological spaces. So very first thing to mention is that I don't even know if this is the correct word to use, because some people use basis with an E, which kind of makes sense because here you're kind of saying this is the plural of the word base, so that makes perfect sense. But I've looked around at various sources and they use a mixture of basis with an I and basis with an E. Even on Wikipedia, if you take a look at the Wikipedia article for this basis of topology or something like that, you'll see that it contains both of these spellings because multiple people, different people contribute to that article, and different people have different ways of spelling it, I guess. So comment down below which spelling you use or which spelling you think is the correct one to use. I'll just use the basis with an I because I is for imaginary number, and imaginary numbers are superior than Euler's number, which is only a real number, unfortunately. But yeah, we'll just stick with this spelling with the I. So what exactly is a basis? Well, it's kind of like a basis for vector spaces if you've taken a bit of linear algebra before. Now, the reason why bases are useful is because sometimes topologies can get very nasty. It could be very, very big, or it could be very complicated. And basis, well, you just pick specific elements of your topology, and those elements must be able to generate the rest of the topology. So very similar for basis in vector spaces. So if you have a vector space V, usually you choose some subsets, let's call it B here, a set of vectors, and the span of B must reproduce a V. And spanning just means linear combination, so you must be able to add and scale multiply your vectors in B in such a way that you recover your whole entire vector space of V. Now in topology land, what happens? Well, we have some topological space M tau. Now tau, you're going to pick a particular selection, let's just call it curly B, and this is going to be your basis, and in here you're only going to have certain neighborhoods or open sets. By the way, I would use subset with this equal sign just to indicate it doesn't have to be a proper subset. But yeah, you only make a certain selection, and this selection must be able to generate the rest of your topology. And what do I mean by generate? Well, in this case, I mean unions. So every single element in your topology must be able to be generated from taking unions of elements in your bases. So that's the general idea and a bit of a analogy with vector spaces, kind of like group theory as well, with generators and all of that stuff. But yeah, we'll jump straight into the definition. Now, you might see a couple of definitions around. You might go to one source, you see one definition, and go to another source, you see another definition, and you might say, well, why are there multiple definitions? Well, it turns out they're all equivalent, and hopefully I'll get to cover all of those in this video and prove them as well. So I'll give you guys this definition. It's quite a simple one, but we can prove all the other definitions from there as well. So let M tau be a topological space. Then this curly B, which is a subset of tau, so tau is my list of open sets. I'm only going to make a certain selection. This guy is a basis of tau. If, now here it comes, if I pick any, so for all open sets U inside my tau, I can choose any points, let's call it P in my U. And there must be able to exist some basis element of B that's in my curly B, so in my basis, such that P lies in B, and this must be contained entirely within U. So this looks like a jumble of symbols now. What does it look like in terms of a picture? Well, let's say this is my whole entire space M here, and I'm going to pick some open sets. Now I'm kind of using the R2 analogy, but really try to think about this abstractly. So I make any selection of open sets U, which is in my topology, and once I have my U, I pick any point, say this one right over here, there's my point. Then I must be able to find some basis B. So B, that's something that would have already been chosen. So I already have a list of neighborhoods here. Can I find one such that it contains P and it's also contained entirely within M? So let's say we find this one that's already in our basis. Does it contain P? Well, yes, it does. And does it lie entirely within U? Well, yes, it does as well. So if this works for all U and for all P inside my U, then B is a basis. So that's the definition. Now it might seem like a bit of a weird definition, looks like I just pulled it out of thin air, but using this one simple definition we can come up with the other equivalent definitions you might see around as well. So I might as well state this as maybe a bit of a proposition. So we mentioned before that if we have a basis, then we must be able to generate every single open set from taking the union of basis elements. So the proposition is that B is a basis if and only if every open set U in my topology, so every U in tau, is a union of sets in my basis that I call B. So if I want to write this out a little bit more mathematically, let's say I have some U that's in my topology here, then I must be able to write this as some union of basis elements. I'll index them by, let's say, bi, and I can run through any arbitrary index that's suitable for the basis I have. So for every single U in my topology, I should be able to write it as a bunch of unions of basis elements. So how do we prove this here? At the moment, it's just a claim that I make. Well, proof. So this is an if and only if statement, so we kind of have to prove this two ways. So we'll go in, let's say, the forward direction first. How does that look? Well, let's suppose the left-hand side is true. So suppose B is a basis. Now what do we want to do? If we pick any open sets U in tau, we want to be able to write it as a union of sets in B. So we're going to pick some open sets U in tau. Then by the definition of B being a basis, which is something we assumed, for all P and U, there's going to exist some B. Now B, it's going to depend on what P is. Now there could be multiple selections of what B could be, but I'll just index one of possibly many by BP. So BP should be in the basis. So for each point in my sets, because B is a basis, I'm going to assign maybe this basis element for maybe another point Q. I'm going to assign this basis element, so maybe I call that one BQ and this one BP and so on. And we have this as such that this P is an element of BP and this must be contained entirely within U. So for each P in my U, there's some BP that works with this. So what can we do from here? Well, so notice since a BP is always contained within U, what we can do now is take a big union over all P in our U of all these basis elements BP. And notice what will that generate? Well, first of all, since all these BPs are contained within U, well, the union of all those should be, again, contained within U. No surprises there. But this actually kind of works the other way around as well, because notice we chose these BPs such that each BP contains P, which means that this kind of holds the other way as well, because every single point in U we can find in this big union. And since that's subset inequality, I guess, works both ways, these are in fact equal. So what did we just show? We showed that if we pick some open sets U, we can in fact express it as the union of basis elements. Okay, and we have to prove the other direction as well. This one's pretty straightforward. So suppose the right hand side is true, so I can pick any open sets of U, and let's say we can write it as the union of a bunch of basis elements bi and I running through some arbitrary index set big I, and of course each of these bi's lie in our basis. Well, notice if we pick any P in U, so given a P in U, what's going to happen? Well, since all these BIs kind of cover U, well, there must exist some BI that's in our basis such that P is contained within BI. And notice a BI has to be contained within U. Otherwise, this equality wouldn't hold, so BI must be contained within U as well. But notice this is precisely the definition of a basis, because I pick any open set U, and I'm able to find a basis element that contains P, and that's also contained entirely within U. So that's the proof done there of the proposition. So basically what this says is that if V is a basis, it must be able to generate every single open set in your topology by unions. So we'll get rid of the proof, we'll keep the proposition there, might need it later. Well, so we'll take a look at one more proposition, which is, I guess, another alternative definition if you want to. This one, I think it's pretty commonly used. It's essentially another way to identify if a specific collection of neighborhoods is a basis. Kind of like this one over here, this tells you if B is a basis. So again, the next proposition is that B is a basis if and only if the following two conditions hold. So first of all, M is the union of all sets in B. So I'll write this as the union of B. So what this really means, if it looks a bit confusing, is that I take a look inside my sets. So B is one big set full of these neighborhoods and so on. And what union of B means is that I just take the union of everything inside this set. That's what the notation means. I'm just a bit too lazy to write it out in words. And second of all, let's say we're given two basis elements. Let's call it B1 and B2. Kinds of like B1 and B2, bananas and pajamas inside B. And also what we're going to do is we're going to choose some points in the intersection, so P in the intersection of B1 and B2. Then there must exist some, let's call it B3, that's also in the basis, such that P is inside of B3, and B3 is actually going to be contained within the intersection of B1 and B2. So in terms of a picture, what does this look like? Well, the first condition, that's pretty obvious. If I have my topological space M here, then if I union all the B's together, then I must be able to recover my whole entire M. Now the second condition, if you want to draw out a little picture for that, well, given B1 and B2 in B, so here's my B1 and here's my B2, and any point P in the intersection, so let's say this is my point P over there, then there must exist another basis element B3 that contains B, and the whole thing is contained within the intersection. So this guy over here, right over there, that's my B3. So if these two conditions hold, then automatically B is a basis, and the converse is true as well. If B is a basis, then these two conditions must hold. So that's something we'll prove. Hopefully it's not too long. So proof. Well, let's do the forward implication first. That one's going to be quite easy. Well, the first condition is just extremely obvious, because by this first proposition here, we assume that B is a basis, which means every open set entails a union of sets in B, but the whole entire set M is also an open set. So we must be able to write M as the union of specific basis elements, but if we union all of them together, then it still reproduces M. So first one is obvious. So maybe the first one I'll just say from proposition 1. And how about condition 2 over here? Well, what we need to show is that we must be able to find this B3 over here that contains P, where P is any random point that we choose. And this just follows from the definition of a basis, because notice B1 and B2, those are both elements of your topology, because curly B is a subset of the topology. So in particular, if you take the intersection here, this is an open set in your topology. It doesn't have to be in the basis, it just has to be in the topology. So this guy is some open sets. We might as well call that U, as we've been doing. And by definition, because we assumed B is a basis, then for every single open set, if we choose any single point P, then we must be able to find another basis element, which we'll just call B3, such that, well, we just have the definition here. So I guess by definition, there must exist some B3 that's in my curly B, such that P is contained within this B3, and this whole entire thing is contained within my open sets, which in this case is the intersection of B1 and B2, and thus we've proven condition 2. So that's the forward implication. Nothing too fancy going on there. Now we'll do the backwards implication. This one, I'm not sure if I have enough room down here, but we'll try our best. So backwards implication. So how does the backward implication work? Well, first of all, just let B be any collection of sets in M. We don't need a topology chosen on M already, so maybe we could just say B is some elements of the power set of M just to start off with. Doesn't really matter. What we're going to assume is it satisfies these two conditions. So we're going to suppose B satisfies conditions 1 and condition 2 over here. And what we want to be able to show is that if a B satisfies these conditions, then a B is the basis for some topology. So this was kind of like just the background over here. We're going to let tau, so we're going to actually construct tau now. What is tau going to be? Tau is going to be the set of all unions of sets in B. Now, if B is a basis for a topology, well, we need to make sure that this tau, the way we constructed it, is a topology, which means we need to check the axioms for a topology. So first of all, we need to check if the empty set and the whole entire set is in this topology. Now, the whole entire set is definitely going to be in the topology because, well, we assumed the first condition was true, which was that the whole entire set can be written as the union of basis elements. But the union of all basis elements is definitely in this set that we just constructed. So axiom number 1 over here is, well, part of it is true. M is in the topology. We also need to check that the empty set is in the topology. Now this one's a bit confusing because the empty set actually need not be in the basis that we have. Now the topology needs to have the empty set, but when we go to choose our basis, we don't need to include it in there. Now, how do we know that the empty set is in this tau? Well, this is the set of unions of sets in B. More precisely, we just need a union over a bunch of these B's over here in a way. Now we could do one union, we could do two unions, we could do infinitely many unions, and nothing's stopping us from doing absolutely no unions, which is exactly what we're going to do. Now if you take a look at the definition of a union, it's the set of all elements that are from one set and another set. But if we're not taking the union of anything, then we're not putting anything inside of this set. So that just gives us the empty set with nothing in it. So the empty sets by this construction is also in the topology. So empty set is in tau. Just don't take the union of anything. Now we're going to skip the second axiom for topology. We'll take a look at the third axiom. What does the third axiom say? It says that this set must be closed under arbitrary unions. Well, by construction, this is obviously true because this contains all the possible unions of sets in B. So if we take 2 in here and we take the union, well, it's already in there. So this is a tick. It's true by construction. And last thing we need to do is check the second axiom for a topology. This one requires a little bit more work. So what I'll do is I'll actually get rid of all this. But essentially, once we've proven the second axiom, then we're basically done anyways. So let's try to prove the second axiom. So the second axiom is closed under finite intersection. So what we're going to do is we're going to select 2 open sets, let's say U and V, that are in our topology, that we just constructed from our basis. Now I probably shouldn't say topology here because we don't know if tau is a topology. We'll just call it a topology in quotation marks or something. But U and V, these are elements of this tau that we constructed. Now if they're elements of tau, then what happens? Then U must be able to be written as the union of elements in B, which is, let's just call them B alpha, as we run through our alphas here. And similarly for V. So V must be able to be written as the union over, let's say, beta of B beta. Now what we want to do now is check if U intersect B can also be written as the unions of these basis elements. So let's go ahead and take the intersection. U intersect V. What is that going to be? Well, we're going to have the union over alpha of B alpha and intersect with the union over beta of B beta. And what is that going to be? Well, we're going to kind of distribute this intersection into these unions a little bit. Might be a bit hand wavy, but I think it's something you can check. I think it's De Morgan's law or something. I might be wrong. But essentially, this just becomes one big union over both alpha and beta of B alpha intersect B beta. And I guess you can show that quite easily because this is just some sets over here. And it turns out if you take the union of things and you intersect with another set, let's just call this Q for now, then this just becomes the union over alpha of B alpha intersect Q. But we already knew that Q was the other big union here. So we have the union over beta of B beta, and then you do the exact same thing in here. So you kind of bring this B alpha next to this B beta, and then you'll get like a double union. So union over, what would it be? Union over beta or alpha, doesn't matter. And then union over beta of B alpha intersect B beta, and that's basically what we have here. Pretty sure it's called De Morgan's law. Maybe one of you guys can correct me on that if I'm wrong. But we'll just take this as it is for now. Okay, so what do we have so far? We have that the intersection of U and V can be written in this form. And so essentially what we're going to do now is we're going to use this second condition that we assumed because we have a bunch of intersections going on, so why not? If I pick any point P, so for all P in this intersection U intersect V, there must exist something of this form that contains my P that I'm interested in. So there must exist some alpha and beta such that P lies in the intersection of B alpha and B beta. But now notice by the second condition, which we assumed was true over here, there must exist some, let's call it BP, because it's going to depend on this point P, and this lies in B, such that P is an element of VP, and this thing lies entirely within B alpha intersect B beta. And hence, notice, I'll put it up over here, since every single point P has a little basis element that goes around it, that means if we take the union of all these BPs here, and we run P through the intersection of U and V, which is where it's from, then what does it recover? Well, I'm running through all the P's in my intersection, so if I union all together, very similar for I think it was the proposition 1 here, this must recover my U intersect V. And you can again do the same argument with showing that one is the subset of the other, and ultimately they're equal to each other, which means U intersect V can in fact be written in this fashion, and this guy over here, this, by construction, is an element of tau. Now, since tau satisfies all the axioms for a topology, that means tau is, in fact, a topology. Which means this B over here, if it satisfies these two conditions, then it must be a basis for some topology, which is the tau we constructed by taking the union, all the possible unions of basis elements. So that's basically all the theory, I guess, that I wanted to go through. So these are common definitions of basis that you might come across. And yeah, they're basically all equivalents because we have all these nice equivalence arrows here. So that's pretty much it, I guess. Maybe just one more remark and maybe an example of bases. Let's do the example first. Let's take a look at the real line. So R equipped with the standard topology. Well, the standard topology, the set of all the open sets is a ginormous set. It's humongous. But what we can do is take a look at a smaller set. Well, it's still infinitely large, but it's, I guess, smaller in a way. We can take a look at a basis. That's just maybe called the standard basis or something like that. I don't know. And this basis consists of the sets of all open intervals a comma b, such that a is less than b. And yeah, a and b are in their real numbers, of course. So the basis is, if this is the real line over here, the basis is just the collection of all possible intervals in this fashion. And intuitively, you can see that you can build any open sets from taking unions of these intervals. And for example, it satisfies the definition of being a basis, because if I pick any open set, let's say this one over here, that's an open set in my topology. I pick any point, let's say this point over here. Well, clearly there always exists a little open interval around it, and that comes from the basis. You can take the second definition as well. You can clearly see that this open set is the union of basis elements. Or you could take the third axiom. Of course, the real line can be generated from the union of all these guys. And given B1 and B2, if you take the intersection, well, already the intersection is nicely an element of the basis anyway, so that's true as well. And now just a final remark, I guess. Well, the thing with the bases is that they're not unique depending on which topology you have, although each basis can only generate one topology. So the picture kind of looks like this. We have up here, these dots represents the different topologies you might have, and each topology might have different bases. Because for example, you could take the topology itself to be its own basis, because it satisfies all these nice conditions up here, but that's a bit useless because usually you want to talk about a smaller set being a basis. So each basis can only generate one topology, so if you go upwards, but if you go downwards, each topology may have many different bases. So with that, that's pretty much all for this video. That's pretty much all I wanted to discuss with bases. We'll use this in the next video. I think that would be on the product topology. We'll mention bases as well. So hopefully this video was helpful. Hope you guys enjoyed it. Until next time, have a wonderful day, and I'll see everyone in the next one. Bye bye.